Assalamualaikum and hello everyone. Today I will be presenting on the topic of finite element analysis FEA of a bicycle frame. Our project is part of the computer simulation course BMKT 3453 under the lecture of Dr. Muhammad Shukri bin Zakaria. Okay, the team members of this presentation are Muhammad Iqmal bin Abdul Rahman, REFDY AIMAN bin ROSLAN, and my name is SYAZANA AQILAH binti AIYOB. Okay, I will be present about introductions. The bicycle frame support part like the giraffe train, pedal, steering, and seat. Although the design has not changed much since the 19th century, new materials like metal and composite have made the frame lighter and stronger. This makes studying materials choice and frame design important in engineering. Okay, the main objective of our studies are to analyze and optimize the structure, performance of bicycle frames under various loading conditions. The second one, identify high stress areas and potential failure zone using FEA. And the third one, compare the performance of different materials like steel, aluminium, titanium, and composites in terms of weight, strength, and cost. The last one, propose design modifications to reduce weight without compromising safety. Okay, for the problem statement, many local bicycle frames still use steel, which add extra weight and reduce efficiency. This can make pedal harder and cause fatigue on longer rides. We want to identify weak points in the frame and suggest the better materials and design change to make the frame lighter, more durable, and cost effective. Okay, for the methodology, we use multiple software tools of different parts of this project. First, we use SolidWorks for 3D models, materials assignment, and basic simulations like stress and displacement analysis to validate the design. Second, we use Inventor for parametric modeling, part and assembly corrections, and stress analysis to predict component performance under different conditions. And the last one, we use ANSYS for advanced simulations, including structure, thermal, and fluid analysis. We match the important models and apply boundary conditions to simulate real-world scenarios. Then, the result, which visualize stress and displacement, it helps us optimize the design. Okay, for general discussion, frame design and geometry. The standard diamond frame design consists of the front and rectangles with key components like the top tube, down tube, head tube, seat tube, seat stay, and change stay. The geometry and tubes selections play a critical role in determining the bicycle performance, including stability, ride quality, and ergonomic. Okay, from general discussions of material used in bicycle frames, different materials have been used in a bicycle frame. First, wood, used in early bike but was too heavy. Second, steel, strong, durable, and easy to repair. Third one is aluminium, lightweight but does not last as long under stress. And the fourth one is titanium, strong and resistant to rust but too expensive. And the last one is composite, very strong, lightweight, and used in a high performance bike. Okay, for this project, we refer to a journal by Ahmed M.Z.2014, which talk about the designs and analysis of bicycle frame. So you can find this journal on SlideShare for the future reading.
Assalamualaikum warahmatullahi wabarakatuh. My name is ROSLAN. Today I will be presenting a computer simulation study for the structural analysis of a bicycle frame. This simulation is essential for ensuring the strength, durability, and effectiveness of the bicycle's design under real-world conditions. Previous research has shown that the evolution of bicycle frame design is greatly influenced by advancement in materials and manufacturing technology. From wooden frames in the 19th century, modern bicycles now use steel, aluminium, titanium, and carbon fiber, each with its own strength and weaknesses regarding durability, fatigue resistance, weight, and cost. Studies have also emphasized that selecting the right materials and optimizing the frame design can reduce overall weight without compromising strength. Finite element analysis, or FEA, allows us to simulate stress distribution and identify high risk zone, leading to better design improvement. Next, we have the geometry of the bicycle frame. This slide shows the dimension from the front view, the chainstay tube, and the seat stay. These measurements are crucial for building an accurate 3D model before performing structural simulations. In FEA, the meshing process is very important. Here, we use three types of meshing: coarse, medium, and fine. A finer mesh generally results in more accurate simulation but requires more computational time. Comparing different mesh sizes helps us find the right balance between accuracy and efficiency. Once the geometry and mesh are complete, a full 3D model is built. This model is used to run structural analysis under different loading conditions that simulate real-life cycling scenarios. We consider three main loading conditions for such analysis, which is pedaling, front impact, and braking. Each condition represents real situations a bicycle might face during use. The goal is to examine how the frame behaves under these forces. For the pedaling condition, a static structure analysis was performed to observe how the frame reacts to the forces applied during cycling. The objective is to ensure the frame can withstand these stresses and meet strength and safety standards. In the braking simulation, we assess the strength, stability, and performance of the bicycle frame when subjected to braking forces. This helps us identify stress concentration, deformation, and safety factors, which are useful for improving the design before physical testing. Lastly, the front impact simulation analyzes how the frame responds to frontal collisions. This helps us identify stress-prone areas and determine if the design can handle typical impact forces. It also supports better load distribution and helps prevent structural failure. For result and discussion, I will pass to my beloved friends, the one main character in our group, which is Iqmal the simulator.
For the simulation, we are using aluminium alloy with the density is 2.77 times to the power of -6 kg per cubic millimeter, and the young modulus is on 71,000 megapascal. Poison ratio is on 0.33. Yield string on 280 megapascal. Shear modulus on 692 megapascal, and the tensile strength is 310 megapascal. For structural analysis, there are three different mesh, which is coarse, medium, and fine. For coarse, the element number is 2004 198, and the total deformation is 1.0259. And for the medium, the element number is 338,375, and the total deformation is 1.0248, and the error was 0.107%. For fine, the element number is on 61,145, and total deformation is 1.046, and the error was 0.019%. verification error. For total deformation, from the journal is 1.45 mm, but while from our project simulation we got 1.0259. For maximum stress, from the journal we got 130 megapascal, but from project simulation we got 39.089 megapascal, and the validation error that we got is 26.25%, and the verification error is 0.12%. For pedaling, maximum stress is 43.057, and the minimum stress is 0.015307, and the difference between maximum and minimum is 43.0417 megapascal. Next, for braking, the maximum stress that we got is 17.841 megapascal, and the minimum stress is 0.0048959 megapascal, and the difference between both of it is 17.839 megapascal. For front impact, the maximum stress that we got is 57.385 megapascal, and the minimum stress is 0.025314 megapascal, and the difference between maximum and the minimum is 57.3597 megapascal. For comparison of the loading condition from pedaling, braking, and the front impact. For pedaling, the total deformation is 1.0248, and the maximum stress is 43.057. While for braking, the total deformation is 0.17326, and the maximum stress is 17.841 megapascal. For the front impact, the total deformation is 1379, and the maximum stress is 57.385 megapascal. For safety factor, the graph shows the relationship between applied force and the resulting of maximum stress. At 489 of force, the stress is at 48.48 megapascal, and the safety factor is at 5.775, meaning the material can handle nearly 6 times the applied stress before failure, indicating a very safe and robust design. The linear trend suggests the material between predictably under load with this range.